Hi, everyone. This is Rob Gray from ASU and the Perception Action Podcast. In this little video, what I want to do is start something that is going to be a little bit of a series, I think, from videos and the podcast, and that is talking about information. What is specifying information? And more particularly, how do we know what the specifying information is for our particular sport? Right. So, what I want to do is focus on two of the most well studied and well known sources of information used for control movement skills, tau and tau dot. I want to go in and look at those in a bit of detail, and then I want to talk a little bit about what it tells us about how we can use it for our sport and some of the implications for coaching. Right. So as I said, I'm getting a lot of questions like this. Right. So in the ecological approach, we talk about representative design. We talk about how it's critical that for your sport, when you're training your sport, that the specifying information is present in your practice. Right. The athlete is using the specifying information that they will use in competition. Right. And I've talked a little bit about what specification is. I'll go a little bit more into it in detail today. It's basically, it's the idea that there's information sources out there that allows us to directly control our actions. It gives us what we need to control our actions without any need for interpretation, processing, bringing in prior knowledge, etc. Right. So that's the idea. Gibson's fundamental idea of specification. Right. So we talk about, it needs to be there. We need to make sure it's there. And a lot of people ask me, well, how do I know what it is? Right. How do I know what should be there in my sport? So what I want to do today is show you an example of a kind of a case study of how you identify specifying information sources by looking at tau and tau dot. And then I'll talk a little bit about how you go beyond that. And I'll expand on this in future episodes as well. I'll get into some other types of skills that we might want to control. So the scenario I want to talk about today, I'm going to talk about American football today as my example, my example to illustrate these things. So what I want to do is show you how you go from a sports skill, something an athlete is trying to achieve on the field or the court or the ice rink, to information and information movement control laws, right? So here we have, imagine you're a defensive player, you're a special teams player, you're going to tackle this guy, right? So at the start of the play, this guy at time t0, he's here. A third of a second later, he's going to be closer to you. He's going to have a bigger image, obviously. Some that one of kind of the relevant variable, obviously, in this situation is time, right? We need to know how much time we have, right, before this person is going to arrive at us. Are they right there, right? And we should just brace ourselves for a hit. Or are they, maybe they're not going to get there until 2 seconds, and we should try to move forward and close the gap, cut off the angle, etc. Right? So that action relevant variable, the first one I'm going to talk about is time to contact, or TTC. Right? So I've tried to illustrate this in this example, and so what I want to do is walk through how in this example we can pick up information about the time to contact directly. So that's the idea. So imagine at the start of the play, the player is running at 30 feet per second, right? And they're a distance of 75 feet away. And I've just picked these numbers. They're not anything special, right? They're just meant so I can, I'm doing math here just to show you that the calculations work out, that it's actually giving you the number, the correct number. It doesn't really matter. I'm not here to try to teach you the formula and things for this, but and if you calculate and use trigonometry and calculate this angle created at the eye of the defensive player by the running back, it's 4.3 degrees, right? So that's the kind of the basic situation. Now, a third of the second later at time t1, the person's still running at 30 feet per second, right? We're going to assume constant velocity here. Now they've reduced the distance to us, right? Because they're coming at us. Now they're only 65 feet away, right? And now the visual angle is going to be bigger, right? That's what's shown in this picture, right? The angle subtended by the player on your eye is going to be much bigger, right? You can think of they're going to block out much more of the background than they did before, right? So in this case, the angle is going from 4.3 to 5.1 degrees. Again, just some numbers to kind of show you how the math works out. Okay. So how do we know how much time we have? How can we pick up information about the time available before the person's going to hit us, the time to contact, right? So we know from math class, right? When you're in math and you're learning about physics, the classic formula of velocity equals distance over time. If you rearrange that, you get time to contact at the point of t1, right, is equal to the distance divided by velocity. That's 65 divided by 30, right? That's 2.16 seconds, right? So at this point, the person's going to arrive at 2.16 seconds from this point, right? So that's information that we can use to time our movements, to set our intention, right? And so on. So it also obviously is related to their speed of running, right? So the fast person running faster is going to have a shorter time to contact, right? So that's all in well and good, except for the fact, right? We are not built with radar guns or range finders in our heads, right? As human beings, we have no direct access. We have no way of knowing the speed the person is running at, right? We do not know they're running 30 feet per second, right? There's no way we can know that. All we can know is that their angle on the eye is changing. Similarly, we have no way of knowing the distance the person was at, right? We do not know they're 75 feet. In research, if you try to get people to verbally estimate the distance of something, especially if it's greater than 50 feet away, they're terrible at it, right? We don't know these things, right? So we, as human beings, cannot use that formula to figure out the time to contact, right? We can't use the distance and velocity, so we're stuck, right? So what's the alternative? Well, how can we get the information we need to control our actions about from this situation, right? So what we can use is, instead of using distances and velocities, which we don't have access to, what we use is visual angles. And this idea, this fundamental idea of tau, what we now call tau, comes first from Fred Hoyle, who in a science fiction, Fred Hoyle was a scientist and a fiction writer as well. He wrote a book about something approaching the Earth, kind of like in the movie Armageddon, if you've seen it. The scientists are trying to figure out how much time they have, but obviously they don't know how big the cloud of gas is. They don't know how far away it is. This was kind of extended in a very seminal paper by David Lee in 1976, where he took this idea and expanded on it and showed it how you can use it to control the actions. And I'm not sure if Dave, it's kind of a very obscure thing, Hoyle's reference. My research PhD supervisor, Martin Regan, kind of found this. It's in an appendix of this novel. So I don't know if I don't know if Dave Lee ever saw it or just came up with it on his own. I wouldn't be surprised if he came up with this on his own. What we're going to see, interestingly, if as a aside, researchers in this area, there's certain people in vision research that are incredibly good at identifying information and picking things. And David Lee is definitely one of them. So the idea here is that the time to contact at T1 approximately is equal to this variable tau, which is equal to the visual angle. Okay, so that's the visual angle divided by the rate of change of angle, right? So how fast it's changing. So before I say where this comes from, let's go through the math. So we're talking about the angle at time 1, which is theta 1, divided by its rate of change. So that's theta 1 minus theta 0, right? So this change in angle divided by the change in time. So it's 5.1 divided by that. The change in time is 3.33 seconds, right? So if you do all those numbers, you get the exact same thing you got from the physics equation, but critically using things that you have right in your visual system, angles. All we have is angles. How could we get the time, you might ask, right? Well, you would assume that our perceptual system is just updating this at a regular rate, right? So it's going to have the time is a constant, right? We don't need to calculate the time. We're updating our perception of time to contact, right, at a regular rate. So it's going to be a constant. That's going to be really a constant variable. Okay. So this is the variable tau, an angle divided by the rate of change of angle. And if you really want to go crazy, right, go look at Dave Lee's work on like general tau theory, which I talked a little bit. I did an episode on the podcast about it. This not only applies to this distinct situation about time to contact, this angle and variable divided by its rate of change is a tau, which a general tau variable, and it applies to lots of other things. But let's just focus on this one here. How did he get that? Well, I'm not going to go into detail of all the math of how Dave Lee derived this equation, angle divided by its rate of change. You can look at his paper and go things in detail. I'll talk a little bit where you can find things, right? And how people came up with these near the end. But I'm just showing you here. So this tau variable, right, specifies time to contact, right? You don't need to do anything processing, calculation. And critically, this is one that people kind of don't grasp right away. Me neither. What we're not proposing is that you have a calculator in your head. We're not proposing that you get the visual angle divided by, then get the time, do all this math in your head. Okay. What Gibson is proposing is that you have in your head a detector for this that picks up this variable directly, right? So it's this specifying information is not created by picking up lower order variables and putting them together, right? It's created by picking up that information source directly, right? So we have a thing in our brain that's directly picking up this higher order information source, not calculating it from lower order ones. Okay, that's a really important thing, right? So critically, now we have a variable related to time, right? A variable that specifies how much time we have before the object's going to collide us, right? So how we used it, how do we use this to control our movement? Well, to do that, what I want to get into is another kind of variant of this called tau dot, right? I want to show you to look at this in more detail, right? So let's think about two scenarios in American football. Okay. So in the both of them, again, you're the defensive back, the special teams player. You want to tackle someone. The first one, you're running towards an opponent that's about to receive a punt, right? And like in this video, this image, right? So what you want to do, right? You want to run up to that player and close the gap to them as quickly as possible, right? You want to be right there to tackle them when they catch it, but you can't hit them before they catch the ball. That's a penalty. That's interference, right? So you need to stop before you hit them, but close the gap as quickly as possible. If you're running, how do you know whether you're running at an appropriate speed to achieve that, right? So now we've created a goal, right? We've created an action problem. What we want to understand is how we can use the information to achieve it, right? On the surface, it would seem like we need to do some complicated calculations and predictions and things like that. Well, here we're going to show you how you can actually do this very easily and directly through specifying information. So that's scenario one. Scenario two, the defensive player, you're saying the defensive player, the player's now caught the ball, right? You're running. You want to deliver a large amount of force on them. So now you don't want to stop before you hit them. You want to hit them while you're on the run and try to cause a fumble, right? But you don't at the same time you don't want to overrun the play, right? So again, we have a different goal, a different intention, but now we're again, how do we know whether we're running when we're running down the field? How do we control our speed, right? How do we know we're running at an appropriate speed, right? So the answer to this is quite simple. Rather than doing some prediction about when the catch will occur and all you really need to do is couple your running speed, right? So we're going to call that V to an information source called tau dot. Okay. So tau dot is the rate of change of tau, right? So in my previous example, we just saw that tau is 2.16, right? Time to contact. We want to look at how fast that value is changing over time, right? So if the person is running at a constant speed and we're standing still, tau is going to drop at a constant rate. It's going to go 3, 2, 1, contact, right? But if we start running towards the player and closing the gap, the tau is going to reduce faster, right? So we're going to have a basic information control law. I'm going to express it really simply. The velocity we run is going to be a function of tau dot. So movement variable, what we're controlling in our movement. This is what we set with the education of intention, right? What we want to control, the aspect of our movement. This is the information source, tau dot, right? I'm going to show you and then we're going to have some calibration constant. And I'm going to talk about that in a second, right? So let's look at what tau dot is, okay? So let's look at our first scenario. So our first scenario, remember, we're waiting for the receiver to catch the ball. We want to get there as quickly as possible, but we want to not hit them, right? So we want to stop before we collide. So again, I put some numbers in here just for illustration and show the calculation, right? Again, it doesn't matter, right? So we're running towards the person receiving the ball at 30 feet per second. So at time 0 or 30 feet, right? But we're decelerating at 5 feet per second square, right? We need to slow down, right? If we're going to stop before we hit them, right? So yeah, at time t0, we're at 30 feet per second. 1 second later, we're at 25. 1 second later, at 20. And by 6 seconds, because of this deceleration rate, we've gone down to 0. Okay, so we've stopped. We can see the distance, right? The distance that we're starting 75 feet, like in my illustration, it's going down to 50, right? Because we've covered what distance we covered, gone down to 30 is 0. So in this exact situation, I picked out the numbers, especially so the deceleration rate and the distance and the speed, so that we're stopping exactly at the player, right? When our velocity goes to 0, we're at the player, right? So what I want to show you, though, is down at the bottom, okay, is what this variable tau dot. So remember tau is the time to collision, right? So the time to collision, right, to shortcut it, right, remember the angles give you the same answer as the physics equation. So if we just do, velocity, distance over velocity, the tau at time 0 is 2.5, right? At 1 second, it's 50 divided by 25, it's 2, right? At this one is 1.5, right? So these are the tau values. These are the time to collisions, how long it's going to take before I hit the player, right, at each point in time. Tau dot is how fast these tau values are changing, right? So you can see it's going from 2.5 to 2 in 1 second, right? What that means is it's changing at minus 0.5. It's going down, so it's a minus sign, 0.5 seconds per second, right? So every second, it's going down 0.5, right? So the value of tau, optical variable tau dot, which you can derive the same way that you got tau through the angles, right, by just extracting, is minus 0.5, right? And so what Lee did wonderfully in his paper, and through lots of examples, and you can look at, is he pointed out this creates a really simple rule. So if the value of tau dot, and I've shown you one example where the value is minus 0.5, you can go through play around with the speeds and distances and get other values, of course. If the value is between minus 0.5 and 0, you will stop very close to the object, okay? If the value is exactly minus 0.5, as I showed in that example, you will stop right at the object so you could kiss the running back, right? You will be your distance will go to 0 at your velocity, right? So all we have to do, right, in our control law is we put in our control law the value of a tau dot we want. In practice, right, we probably wouldn't want it to be minus 0.5 in real football. We don't want to get that close, right? So we might set it at minus 0.3, right? So all we have to do is run our velocity. If the tau value starts to get too negative, right, we speed up. If it starts to get too positive, we slow down, right? So we're basically have a simple control law, right? We just set our running speed, couple it to tau dot, and adjust based on our goal, right? So in setting our intention, what we're going to do is set the tau dot value that we want to run around, right? So it's great if it gets too negative, we're going to speed up. If it gets too great positive, I'm not sure if I said that the wrong way around last time, slow down, right? So that's the first tau dot. And I'll come back to this. There's a few important points about that. So that's the first tau dot rule, right? So notice here, we don't know the distance to the running back. We don't know their speed. We don't know any of that, right? Also, all through visual angles, which allow us to get tau and tau dot, we can simply control our running speed. We can adjust our running speed to achieve our goal. All we have to do is set up that control law, be sensitive to tau dot, and put in the right value for our intention, right? Very simple. Here's another example. Imagine we wanted to, this is scenario number 2. The person's already caught the ball. Now we want to deliver with force. We want to arrive with force so we cause a fumble. Here's an extreme example of that. What we're going to do is not decelerate at all, right? We're going to keep our velocity 30 all the way through. Obviously, when we arrive at the player in the distance of 0 feet, we're going to still be going 30 feet per second. So we're going to have an incredibly hard collision with them if we hit them. The taus in this case, you can see the tau is going 2.5, 1.5, 0.5. So the tau dot, how much tau? So dot is if for those mathematically inclined, it's a symbol used to represent a derivative, right? So tau dot is the rate of change of tau is 1, so it's minus 1. So you can see it's got more negative, right, than my last example. So it was minus 0.5, now it's minus 1, right? And from David Lee, again, you can play around with all the numbers and you can come up with a control law. if the value of tau dot is between -1 and -0.5, you're going to hit the object while you're still moving, right? If it was -0.5, you'd stop right at the object. If it's any more negative than that, right, you're going to hit it with force. The closer you get to -1, right, the more force you're going to deliver, okay? So again, we can have a simple control law, right? Now my intention is to cause a fumble. I have a new goal. I don't have to do all these complicated things, right? All I have to do is have that control law. Velocity equals is a function of tau dot. Select the tau dot value to be something like -0.8, right, in my goal, right? And adjust my running around that. So if it starts to get more negative, I slow down a bit. Start to get more closer to -0.5, I speed up, right? Again, very simple coupled law, right? The other advantage, so another thing that's important to know about this is these simple control laws are incredibly powerful. So that simple control law, my running velocity is a function of tau dot with some calibration, right? This allows me to adjust my strategy, my control based on some what we commonly refer to offline information. So tau and tau dot are online information, right? They're available when we're running, right? When the event's happening, the angles are changing, they're varied. Imagine we're a special teams player, and during the first two attempts we've had at kick, punts, the person is a really shifty, really elusive player. The person that comes to mind, I'm old school, is Devin Hester, who's a great punt returner. So imagine the first two times that you tried to tackle them, they got around you, right? So now you have experience of facing this running back. So what you can do in your control law is you probably want to turn it down a little bit, right? Instead of trying to have a tau dot of, say, -0.9, you might want to use -0.6. Why? You don't want to have that try to generate such a hard contact because you're increasing the chance that they're going to get around you. So learning through experience with a particular running back, also the certain times of the game where you don't want to allow a big play, right? All you have to do is adjust your control law, change the calibration, right? You don't need to have some Bayesian model where you predict this happens, that happens. All you have to do is let experience with the environment change the control law, right? Change the values used, change the calibration, very simply. So it's very easy to pull in offline information that it's basically longer time scale information, right? It's not happening in the moment. It's your experience over time with this running back, right? So that's an important thing, I think, to point out. The last example I want to show you is kind of the third law that Lee came up. Imagine now we're accelerating really hard at 10 feet per second. Right now, our speed's going 30, 20, 10. In this case, we're going to stop 45 feet in front of the running back, right? So this is kind of a silly example, but it might apply to other skills, right? Where you really want to keep the person, right? So now you can see the distance is going 75, 55, 45. Tau dot is going 2 points. So tau dot is now positive, actually. Your time to contact with them was 2.5, right? Because at this time, when you're stopping, the time to collision is going to infinity, right? You're never going to hit someone. So the time until you hit someone is going up to infinity, right? So tau dot is actually increasing. The tau is actually increasing. So it's positive 0.25, right? So the third control law is that tau dot is greater than 0. You will stop moving a long distance from the object. The greater the number, the further away you will be. So again, you can create a control law, okay? So before I go on to some of the summary and implications, I want to point out a couple of things about this, okay? First of all, notice, right, at no time, so when we establish this control law, which allows us to achieve our goals, right, using information, velocity is a function of tau dot with some calibration. Notice at no time, right? First of all, I want to point out these rules are not explicit at all, right? You're not thinking, the tau dot's 3 now, or tau dot's 0.1 now. I need to do this, right? It's all implicit and internalized in our control law, right? The only thing we do is kind of set the goal, we set the value, right? And again, it's not explicit. We don't, my value is going to be 0.8, right? There's no conscious, right? This is all developed through experience, right? We learn through experience that I wanna hit the player hard. This is how I achieve that in the control law, right? So in no sense is this explicit cognitive, right? It's a simple coupling between perception and information, right? Right. So I'll say this in the end, right? But teaching an athlete these tau dot rules, right, would be as nonsense, right? You can't implement them cognitively, right? You have to learn them through experience with your environment. Okay. The other thing I want to point out, and this applies to tau as well, notice that at no time is the athlete actually judging the variable, right? At no time do we know that the time to collision is 2.5, right? So it's not knowledge. We don't know things about the environment. We don't know that the person is going to hit us in 2 seconds or judge that they're going to hit us in 2 seconds. We create an information control law that uses variable related to that information, which is completely different, right? So we're not making explicit judgments, quantifying the outside world. We're establishing a relationship to it based on the information source that allows us to achieve our goal, right? We don't need to know. We don't ever need to know what the time to contact is if we have established the right um, goals, right? We established the right information movement control law. So that's kind of, these are fundamental things I think people miss, right? So through experience, I learn that if I run, I educate my attention, right? So I learn, oh, this tau dot variable gets me what I want to do. Again, not in an explicit way, right? So again, I think that's important to emphasize. So let's get to some summary, okay? So if you believe Gibson and you're a supporter of direct perception, you believe that there's always information sources like tau and tau dot available in the optic array that specify the variables we need to control our actions, right? So specify things related to time, to size, to the how big a gap is, right? Notice these are action related variables, right? They're not general things about the world like distances of things, right? They're action related variables. How much time do I have left? Am I slowing down at the right rate? Right. And and so tau is telling you the time to contact, which, I gave a football example today. Obviously, if you want to intercept an object like hitting a ball, that variable is going to be critical because it's telling you how much time you have to, you need to get the bat to this point in this amount of time left. Right. And tau dot, really interestingly, and I encourage you, John Wan also has a wonderful paper on tau dot, right? It tells you about the type of contact or collision you're going to have. Are you going to have a soft collision, a hard collision? And in Dave's original paper, he talks about driving, applying this to driving. Okay, so there's always these specifying information sources out there that we can use. All we have to do is establish a relationship with them. That's the fundamental idea of direct perception and specification. So to control actions, we simply need to become attuned to this information and couple our movements to it in an information movement control law, right? So again, it's establishing a relationship. It's not learning to predict, judge, know things. It's developing a relationship. I showed this example, offline information, right? So information about an opponent's tendencies or the game situation or any of these things can easily be incorporated into control lies by adjusting the value you use to couple in your coupling law and adjusting the gain, kind of that calibration, right? So they're easy to incorporate. We don't need fancy Bayes algorithms and predictive processing. We can easily get those things in this way. Okay. So 3, on to the kind of the question I started with. I realize I really haven't answered your question for, if that was your main question, how do I know, right? How do I know what the specifying information is for my skill? Well, in reality, it's not very easy, right? It's not very easy because, well, you have to start with a task analysis. What is the actor trying to do? What are their goals? What are the action relevant variables? Do they need to know how much space they have? Do they need to know how much time they have? Are they trying to intercept? Are they trying to avoid, right? So we start with that. And then the step that's kind of tricky, right? You need to do David Lee did a mathematical analysis of the relationship. Okay. And he, calculated those angles and things and did trigonometry and figured out all these things. And that's not always easy. I know that's beyond a lot of coaches. I've done some of this. It's not always easy. But luckily, what I'll point out is For almost any sports skill you can think of, this has already been done for you if you find the right papers and the right articles and books, right? Because, I've shown you some simple examples here. Someone heading on a collision course with you, right? There's also examples when what happens when they're going off at an angle? What happens when they're going in a curve path? What happens when you want to, instead of hitting an object, you want to hit a gap, or you want to make it through a gap? All those things are out there, right? If you look in the research, people have done the work, the mathematical, the task analysis to that you could apply to your sport if you were so inclined to figure out what the exact specifying information and control laws were. And then if anyone is really interested for their sports skill, we can work together to try to get into more. I can help you find the resources and do some of the number crunching if you're so inclined. Okay. Here are some really good examples of it. David Lee's 1976 paper, right? The theory of visual control of braking is one of the most important papers in action control. It's one that introduced tau and got people off and running. Another one of my favorite is James Todd, visual information about moving objects. That's where a lot of the kind of the fly ball, some of the things and things are. And then a really, if you're really, I would only recommend this if you're a bit mathematically inclined. James Cutting wrote a book in 1986 called Perception with an Eye for Motion, which is a lot about optic flow and different variables with controlling your own self motion. It's very dense read, but so I mentioned, throughout the kind of history of vision research, there's been some people that are really skilled at this ability to pull out these specifying variables like tau and tau dot. Like David Lee is a genius in this ability. Is unbelievable. He can sit down with you and there's other people, like if you talk about more spatial things like perceiving slants and object shapes. There's Kondrik and Van Dorn, right, are two of the people, and I think we hopefully we got more of these people because it's as I said, it's quite a skill. But this is a place to start. Yeah, as I said, if you have a specific sport or skill you want to really get into, contact me and we can work together on that. Right? So, what are the implications for coaching? Right, as I said, you can't explicitly teach athletes how to use an information source, what an information source is. So sitting down with an athlete and going through this thing I talked to, okay, so tau dot is the tau rate to change the tau based on the angle. Here's the three control laws. If your tau dot is 0.7, like that's a waste of time, right? You can't implement it that way, right? All you can do as a coach is create environments and practice that help an athlete educate their attention to it, right? Pick up this tau dot information, right? And realize, not in a conscious way, that it's effective for controlling velocity, and learn to couple your movements to it. How do I do that? Well, as I said, you could go to the trouble of identifying the specifying information. Now, as I said, there's tau and tau dot. There's also tau of gaps for sports like soccer and things like that. Um, this would be useful, I think, because you can calculate how much it's varying in the different practice activities through video or simple analysis. You could also perhaps figure out what control laws the athlete is using and try to change them. But I know this is not, that's going way above and beyond what a lot of coaches want to do. But at minimum, right, what we need to do is encourage and create practice environments mostly through variability, through use of constraints that encourage the athlete to educate their attention to tau dot, right? What you don't want to do at the very minimum is create a restricted, decoupled, low variability practice environment, or use those a lot too much, that allow the athlete to develop non-transferable control laws. And I've talked a lot about this in the past, right? If I'm always hitting off a pitching machine that's throwing at a constant velocity, I can time my movements based on the size of the ball, right? Instead of tau, right? I can time my movements based on, the things like that, right? So we want to try to avoid that. We need to allow an athlete to learn to develop the velocity equals function of tau dot, right? To control their running speed through our practice design. And we can, as I said, variability and effective use of constraints is the key. Okay, that's it for this little video. Hope you enjoyed it. So this will walk a little bit down the information path. As I said, I'm going to go into this in more detail, talking about the optic flow, kind of some extensions of tau of gaps, these kind of things. So we'll get into that more in future lectures. So thanks for joining me. Cheers for now and keep them coupled.